Okay, everybody, you're gonna have to grab an extra large latte for this one. We're looking at 3.5. First thing is to try and understand this diagram. What we've got is reinforced concrete. So concrete block like that, and then along the lower edge I've got an array of steel reinforced rods there. How they would look in real life would they be maybe a bit like corkscrews, or sometimes a bit twisted, because you heat them up and let them set, which will cause compression, so they're putting the concrete into compression all along the lower edge. So now if you interpret this diagram here, this is turning into here, so we're turning into here. We've got a bending moment going like that. Now I'm not too sure whether Arnold's done this, but I'm going to ignore the lower section because I'm going to assume that the compression from the steel rods is dominating the stress in the lower half of this concrete beam. So if we look at the concrete beam from side on now, the first thing I'm going to be assuming is that we can simplify this down. We've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I can simplify it down like this. And ignore this concrete section here, because so that's going to be my first simplification. We haven't been told how wide this thing is. We're working in with bending that for each 300mm width of slab. So I guess what we can do is we haven't actually been given a width, so we could work in terms of 1 meter. And say that 1 meter divide that by 150. How many rods would that be then? So if we start there, just a bit above, I'd get 1 in. 1, 2, 3, 4, yeah, so that would be the same as that number, so 6.666. So I'm going to have in effect 6.667 rods in this 1 meter. Yeah, that makes sense. And we've got a bending moment of 4.5 0.5 kilonewtons for each 300 millimeters width of slab. So I've done 1000 millimeters, divide that by 300, multiply that by 4.5. So I've got 15 kilonewton meters of bending. That's my M there. Right. So I've done that. Now let's think about what the stress profile is going to look like in this problem. So we're going to have this row of steel rods. We've got the concrete, and our stress profile will have this will well, the steel will be in tension, and then the concrete will be all in compression or zero. So here I'm going to imagine I'm going to have the stress go crazy where it's in the steel rods. Then I want the stress to basically stop at the neutral axis, and all through this will be like during this concrete section here, and then drop nice and linearly in this homogeneous section here. So my argument is going to be that all the tensile stress will be picked up by the steel rods. Below the neutral axis, wherever that might be, we're going to have no stress, and then above the neutral axis the compressive stress is going to drop from 0 linearly to a maximum compressive stress. So that's what my profile is going to look like. So my problem, if I now draw this as if this was a homogeneous concrete problem, I would end up with that we've got a really wide bit of concrete at the bottom. We've got nothing here, and then we've got a little bit of concrete at the top, which is the same as this width here, which I'm taking to be 1 meter. So I've got that width there, and then I've got this bit of super duper long concrete, which I will say is approximately going to be the N times by the area of the steel rods. Okay, I take this to be my base distance. So the distance from here to here is going to be the X is going to be where we have the neutral axis. Do I need to label up anything else at the moment? I need to know the distance from here to where the steel rods are, which is going to be 100 millimeters. Let's work in millimeters. So this will be 1000 width, 1000 millimeters in width. Right. So the first thing I want to do is try and establish where this neutral axis is. So I know neutral axis is given by sum of areas times by their centroids divided by sum of areas. So what I'm going to do is be a bit crazy, and although that's my datum position to find this x, which is going to be the neutral axis, I will set my neutral axis to be here, and I will set that to be 0. Yeah, that makes sense. So y can go upwards. To get to the centroid for this block of concrete, I need to go half the distance of x. So its area is going to be 1000 millimeters width. It's going to have a depth of x, and to get from here to here it will be half x. So now y is going upwards, so to go down, to get from here to here, what's that distance? Well, it's minus, because we're going in the opposite direction to y, below the neutral axis, so there's a minus there. The area of this section of concrete is defined as n times the area of the still. What we're relying on here for my other approximation is that n is going to be very large. Well, it's not crazily large, but it is quite large. Multiplied by 100 millimeters, which is to get from here to here, take away x. Okay. So therefore we've got 500 x squared, and notice that I've set y to be such that this is 0, so that's equal to 0. Well, that's equal to 0, so this is going to be negative. So minus n, which is 200 Young's modulus for steel, divided by 25 Young's modulus of concrete, times by 6.667 rods, times by pi, we're working in millimeters, 16 squared divided by 4. Okay, going to have the same thing here. So this times this, then that'd be an x. This times this times x, so that'd be a positive. And then I've got this times that, so that's straightforward, so that's going to be minus 100, same thing, 200 divided by 25, 6.667 pi 16 squared divided by 4. So let's find out what that number is. And that equals 0. So we've got 500 x squared, 200 divided by 25 times by 6.667 times by pi times by 16 squared divided by 4. So plus 10,724 x multiplied by 100. Because minus 1,072,384 equals 0. So let's find out what x is. X equals minus b, so minus that number, plus or minus has to be plus, plus b squared take away, so that's going to be plus 4ac divided by 1,000. Right. So minus 10,724 plus square root 10,724 squared plus 4 times 500 times by 1,072,384 divided by 1,000. So that gives me x equals 36.81 millimeters, which kind of sounds about right. Didn't expect it to be a bit less than 50. Right, what am I doing now? So now I've got the position of x, I can go on to find what the second moment of area is of this structure. So remember, that's going to be the sum of the sections BD to the power 3 divided by 12 plus A times by their distance from the, sorry, make that H, times by their distance from the neutral axis to their centroids. So if we do the top one here, that's relatively straightforward. B is 1,000. D is the depth, which is the x, so that's the 36.81 to the power 3 divided by 12. And then we've got its area, which is straightforward again, so that's 1,000 times by 36.81. And then the distance to its centroid is half x. So that's going to be 18.41 squared. Okay, now for the rods, we'll make the assumption that, well, notice here what we've got for the rods. You're going to have a very small diameter. You've got in effect something here which is of the order d to the power 4 divided by 12. Here you can have d to the power 2 of the order, that is d to the power 2 times by h squared. So you've got something here which is d to the power 4-ish, and here you've got something d to the power 2-ish times by a big number. So I'm going to completely ignore that part of the second moment of area and just use this part, which is going to be N A of the steel remember we're looking at the concrete structure multiplied by the distance from here to here. Right, so that's 100. So the distance to the bottom is going to be 100, take away 36.81. So we've got 100, take away 36.81. So that's 63.19. Right, so that is 63.19 squared. And this number here is this value here, so it's that value there. So that is altogether, this is going to be 10,724. So we're working in millimeters here. Right. So let's stick that all in the calculator and find the second moment of area. So 1,000 times 36.81 to the power 3 divided by 12 plus 1,000 times by 36.81 times by 18.41 squared plus 10,724 times by 63.119 squared. So I make that to be 59.45 times 10 to the 6 millimeters to the power 4. Right, so I have now got my I. Now what do I do? I'm now going to look for the stress that's in the top section. So stress is going to be M y to top divided by I. So the M is 15,000. If you remember that, it's because I'm assuming I'm 1 meter, so I'm not doing per width or anything. So that's 1 meter. Based on a width of 1 meter, we've got 15,000 kilonewton meters. The y to get to the top is going to be the x value. So that's 36.81 times 10 to the minus 3. And the I, we'll convert that into meters, easy enough. 59.45 times 10 to the minus 6. Make the 6 into a minus 6. Nine point 3 megapascals, and that's in compression. It's not very much actually. I suppose that's okay. Right, now let's work out what the stress is. That's the stress of the concrete at the top. Now let's work out what the stress of the concrete for this kind of flat plate concrete at the bottom. So we'll just take that bottom bit to be the same distance from here to here. So that's going to the bottom, that's going to be this number here, the 63. So that's the concrete at the top. So for the concrete at the bottom, we're going to have m y bot divided by I. Same sort of thing, 15,000, 63.19 times 10 to the minus 3, all over 59.45 times 10 to the minus 6. So that is 15.94 megapascals. So that's the stress in this imaginary problem here. But we want to now go from this imaginary problem back to this problem here. Even this isn't the real problem because we've got concrete at the bottom. So we are now going to look at what the stress is in terms of the steel. So to get that, we have to then reduce this by the ratio of 200 divided by 25 to get back to the steel. So that will then increase this stress, and the stress in the steel will equal the stress in the concrete at the bottom times by the n factor, where the n factor is 200 divided by 25. So that then becomes 127.5 megapascals. Okay, and that would be the sort of thing I suppose we would hope to be getting. So basically a lot of this bending moment is taken up in the steel, and the steel is going to give us a big tension. Steel likes to be in tension, and we're going to get no concrete in tension, and we're going to get minus 9.3 megapascals in compression. If we did a ratio of those two extremes, 127.5 divided by 9.3, we see that we're going to get a ratio of about 14 in terms of the stress that's in the steel compared to the stress that's in the concrete, which is a good thing, you know. How long did that take? Oh, not long.